Here we are asked to determine whether an integral is convergent or divergent. And what makes this integral a little bit unusual, of course, is that the upper bound is infinity. And so when you have an upper bound of infinity, you have a special type of integral known as an improper integral. And we're going to evaluate that in a very special manner. Perhaps the first thing we can do is to notice this constant of 27. We can factor that constant out to the front of the integral. So we can rewrite this as 27 multiplied by an integral from 1 to infinity of this function e to the negative radical x all over radical x dx. The next step we're going to do is to replace the infinity with a t. You can choose any variable you wish, but I believe the textbook tends to use t. And what we'll do is we will allow t to approach infinity. So in other words, we're going to do the limit as t approaches infinity of the integral from 1 to t, and then we have our function. This is essentially the same thing as the original integral. It is just a more formal way of approaching the problem. And next thing we need to do, of course, is to evaluate the integral of our function. And so usually what we do is take an aside and evaluate the integral, and then we can come back and evaluate the limit itself. So we'll take an aside and we'll drop the bounds, and we're basically just trying to evaluate the integral of our function. And a lot of times in these problems, you'll find that using a U-Substitution can be a very effective method for evaluating the integral. So we're going to try that. And typically, when you have an exponential function, it is advantageous to let u equal the exponent of that exponential function. So we're going to let u equal negative radical x, which of course is the same thing as negative x raised to the power of 1/2. We will then differentiate with respect to x, so we'll have du is equal to negative 1/2 x raised to the negative 1/2 dx. And then what I like to do in my U-substitutions is solve for dx. And so in order to solve for dx, perhaps the first thing we can do is to multiply both sides of this equation by negative 2. And the reason that works is because negative 1/2 multiplied by negative 2 is just positive 1. So these effectively cancel each other out. So now we have negative 2 du is equal to x to the negative 1/2 dx. Next, perhaps we can multiply both sides of the equation by x to the positive half. Now the reason this is effective, because when we multiply x to the negative half by x to the positive half, we would add these exponents. So negative 1/2 plus 1/2 is, of course, 0. You would have x to the 0, which is just 1. Any quantity raised to the power of 0 is just 1. So you're left with 1 times dx, which is just dx. So on the left side, if we scramble things a bit, you'll have negative 2x to the half du. Now we make our substitutions. So we're going to have the integral of e raised to the power of u. Remember, we let u equal negative radical x. This will be over the square root of x. And then this dx that was in our problem, we're going to be substituting in this expression right here. This was the reason that we had solved for that dx. So we'll have negative 2 multiplied by x to the half and then du. Now, let's recall that x to the power of half and the square root of x are the same thing. And since one is in the numerator and the other in the denominator, they can cancel. We have negative 2 that can be factored out. So we have negative 2 times the integral of e to the u du. Now, the integral of e to the u is just e to the u. So this ends up equaling negative 2 e to the u. And then we recall we had let u equal negative radical x. So this becomes negative 2 multiplied, well, we don't need to write it that way. We can just do negative 2e raised to the negative radical x. So that is the integral. Now, that was computed as an aside. Let's not forget that the main problem that we were working with was this entire problem right here. So after you evaluate the integral on the side, you want to return to your main problem and then use the result of that integration you conducted on the side. So in other words, this integral right here, we can now rewrite this using the result we just obtained. So that's going to be negative 2e raised to the negative radical x. And it's going to be evaluated from the lower bound of 1 to the upper bound of t. Don't forget in front, as I notice students often do, you still have this limit as t approaches infinity. And furthermore, don't forget that we actually had factored out a 27. So really, this is what we have. And now what we're going to do is plug in our bounds. You recall that the upper bound gets plugged in first. So we'll do that. We'll have the 27 multiplied by the limit as t approaches infinity. And then we'll plug in that upper bound. So you're going to have negative 2e to the negative radical t. Then you subtract what you get by plugging in the lower bound. So we're going to plug the lower bound in next. Now be careful here. You're going to end up, when plugging in the lower bound, with a negative 2. So don't forget that extra negative sign there. E raised to the negative square root 1. Now we just need to evaluate the inside of these brackets right here. And basically what you can do is allow t to go to infinity now. So we're going to basically plug infinity in for t. And one way of thinking about that is as follows. You'll have negative 2 times e raised to the negative square root of infinity. This double negative right here is going to make a plus. And then you'll have 2 raised to e to the negative, and then the square root of 1 is just 1. So it's just e to the negative 1. Now what we need to figure out is this quantity right here, e to the negative infinity. Let's just pull that off on the side and talk about that. It was actually e to the negative square root of infinity, but the square root of infinity is still infinity. So it really is easier to just think of it as e to the negative infinity. This is the same thing as 1 over e to the positive infinity. And if we let this denominator, if we let e go to infinity, you're going to get a very large number. So this basically goes 1 over infinity. And if you take a finite number like 1 and divide it by an extremely big number like infinity, that is going to approach 0. I always like to think of that as taking $1 and imagining that I'm dividing that among everyone in the world. And if I took $1 and divided it amongst everyone in the world, then basically everyone would get nothing. So you can think of it that way, perhaps. Regardless of how you think of it, this is going to go to 0. So now we have 27 multiplied by negative 2 times 0 plus 2e to the negative 1. This entire quantity right there goes to 0. So now you have 27 times 2 e to the negative 1. 27 times 2 is 54. So you get 54 e to the negative 1. And if you prefer, you can write that as 54 over e to the positive 1. So that would be the result of this integral. And recall that the question said to determine whether the integral is convergent versus divergent. The answer here is convergent. And the reason it's convergent is because the limit of the integral ended up equaling a finite quantity, like 54 over e. This is a finite number, and therefore it is indeed convergent.